Hey everyone, and welcome to This Explainer. Today we're dissecting a fascinating, highly specialized, domain-specific language called Merv. We're going to map out its exact, somewhat unique place in the broader programming landscape. We're not just going to look at it as a random grab bag of weird features either. Instead, we'll see it as a coherent, synergistic whole that's designed for a remarkably specific environment. Let's get right into it. Here's a quick look at our roadmap. 1. A niche in the landscape. 2. The least authority ancestry. 3. Concurrency, actors, and pools. 4. Data without traditional structures. 5. Ownership and dimensional safety. And finally, 6. The synergistic whole. All right, Section 1, a niche in the landscape. Let's define our boundaries before we actually start exploring the features. To kick things off, we really have to establish exactly what MERG-J is not, just so we don't accidentally oversell it. Unlike general-purpose languages, your Pythons, C++, or Rusts, you are absolutely not going to use this to build a desktop app or write a quick web scraper. No way. It's a highly opinionated DSL with a very rigid structural target. It deliberately makes some pretty painful trade-offs just to excel in one incredibly narrow domain. Specifically, it's explicitly tailored for the needs of non-Layer 1 functionality within an Innuendo Stack ecosystem. It was built from the ground up to safely manage Layer 2 nodes, bots, and backends exclusively within its own ecosystem. It's a specialized tool for a very specific, security-critical job in the Web 3.0 space. Nothing more, nothing less. Moving right along, Section 2, the least authority ancestry. Time to trace the lineage of this secure design. So the absolutely crucial point to understand is that MERG relies incredibly heavily on the Object Capability Model, or OCAPS, to strictly manage permissions and data flow. If you aren't familiar, OCAPS is a security model where objects interact only through explicitly granted authority. It completely prevents unauthorized vulnerabilities. In MERG, all ambient authority is strictly modeled as a directional acyclic graph. You don't just, import the whole world into your namespace. You are handed exactly what you need and absolutely nothing else. When looking at its predecessors in the language landscape, MERG-E actually pays a lot of tribute to the 1997 E language for that least authority spirit. But it actively sacrifices E's persistent VATs to achieve its own parallelism goals. E focused heavily on these long-lived blockchain-backed execution environments, right? But MERG-E needed to balance that pure security with the messy realities of modern, bursty parallel workloads. So it made a very practical compromise. Okay, Section 3. Concurrency, actors, and pools. This is all about managing execution and state safely. Now you might be wondering, and it's a super common problem in secure systems, if we restrict authority and shared state so severely, how on earth do we actually get anything done concurrently? Well, the solution lies in actors. The workflow is pretty strict. First, you define a long-lived actor callable. Then you create an actor pool. Next, you send your invocation context to a shared message box. And finally, a scheduler distributes those tasks via round robin. What this means in practice is that consecutive calls run sequentially with persistent state within the individual actor, but the pool allows the runtime to safely distribute the total load across available workers. This approach creates a really stark contrast with languages built for massive concurrency out of the box, like Erlang or Elixir. MERG utilizes what they call zero-assumption parallelism. This literally means your code acts merely as a set of hints. The underlying runtimes that interpret your code could range anywhere from basic single-threaded Python task pools used for basic scripting, all the way up to bursty CPU thread targets or even complex cycle kernels. It deliberately does not assume there's a massive concurrent engine waiting underneath. Which brings us to Section 4, data without traditional structures. Let's strip things down to the bare essentials. To keep the language small and simple to implement, MERG completely abandons the common data structures we all know and love. It relies almost entirely on just 3 core types: arbescent DAGs, that's directed acyclic graphs, data frames, and basic scalars. Yep, that's essentially the whole shebang. Their philosophy is basically this. If a directional acyclic graph can map authority and act kind of like a struct or dictionary, and a data frame can handle your collections, then MERG just flat out refuses to add classes, structs, dicts, or lists to the language. It forces you to use the absolute minimum number of abstractions. It is a stark, very intentional contrast to the massive, rich standard libraries you'd find in traditional programming languages. Next up, Section 5, ownership and dimensional safety. Time to look at how it enforces rigid physical and memory boundaries. C++ developers, brace yourselves, you might recoil a bit at this one. Mergy defaults to a move and steal ownership model. It's actually really similar to what the C++ committee originally considered for the now deprecated auto_PR. By default, ownership is transferred, not copied. You literally have to use explicit modifiers if you want to share or borrow mutables. It forces you to write safe code simply by making the unsafe options incredibly verbose and annoying to type out. We also see a really deep focus on physical safety through dimensional type systems. Now, this isn't a completely new idea, right? Taking the torch from languages like Ada and VHDL in the 80s, Fortran in the 2000s, and F-sharp's units of measure in the 2010s, Merc-E evolves this concept specifically for its own modern data flow needs. But there is a key difference. Where a language like F-sharp erases units early in the compilation process, Mergu uses standalone tensors to physically isolate them into completely mutually exclusive systems. We're talking systems like SI, Planck, and a special demote system. This ensures absolute compile time type safety. You literally cannot accidentally mix a length with a temperature, and there is no way to implicitly convert between SI and Planck units. It just won't let you. And that brings us to section 6, the synergistic whole. Let's see how all these constraints actually become a cohesive engine. See, Mergo isn't just a random collection of borrowed ideas. Object capabilities limit your access, move semantics prevent your data leaks, actors manage your safe concurrency, and dimensional types enforce the physical rules. These strict DAGs, move defaults, and dimensional types synergize entirely to force secure, side-effect-free data flows. If you pull one piece out, you break the whole ecosystem. So it's not a pure actor language, and it's not a pure object capability language either. It is a highly practical, opinionated merge of these concepts, designed to work seamlessly together as one single engine. So I'll leave you with this question. Are highly opinionated, strictly constrained DSLs the future blueprint for secure Web 3.0 architectures? As we wrap up this explainer, I really want you to think about the future of secure system design. Sometimes, actually taking away general-purpose features is the absolutely crucial step to guaranteeing safety in a specific domain. Thanks so much for joining me today, and keep exploring.